We continue our work with hypothesis testing by focusing on problems where we're testing a claim about a population proportion. This section describes a complete procedure for testing a claim made about a population proportion, which we will denote with the lowercase letter p. We illustrate hypothesis testing with the p-value method, the critical value method, and the use of confidence intervals, although we will highlight the p-value method and the critical value method as the preferred methods. The methods of the section can be used with claims about population proportions, probabilities, or the decimal equivalents of percentages. So any problem that refers to a proportion, a probability, or the decimal equivalent of percentages will all fall under this same category. Let's review some notation that's going to make an appearance in some of the calculations that we will perform. As always, the lowercase letter n will represent our sample size or the number of trials. In this case, the lowercase letter p is going to denote that unknown population proportion. P is the value used in the statement of the null and the alternative hypotheses. P hat is going to stand for the sample proportion. So that hat symbol is very important because it differentiates between sample results and what we are hypothesizing regarding the population results. The sample proportion p hat can be calculated as x, which is the count in the sample, divided by the sample size. And finally, q is going to be 1 minus p. So p is the hypothesized value of the population proportion. Q is the complement of that number. For these problems, the test statistic that we are going to be using will be a z-score. So all problems that have to do with proportions, probabilities, or percentages will fall under the standard normal distribution, which is the distribution of z-scores. The test statistic is going to be calculated as follows. It is going to be the sample proportion minus the hypothesized value of the population proportion divided by the standard error, where the standard error is the square root of p times q divided by n. This p here is the claimed value of p that appears in the hypotheses. Q is 1 minus that number, and of course n is our sample size. We are going to be focusing on two methods for making a decision about our hypothesis test results. We are going to be using the p-value method or the critical value method. P-values are areas under the curve. For a left tail test, it will be the area in the left tail to the left of wherever our test statistic falls. The p-value, if we have a right tail test, will be the area to the right of whatever the test statistic is. And in the case of a two-tailed test, the p-value will be twice the area of whatever tail the test statistic falls in. We can use our TI-83 and TI-84 calculators to also find the p-values, although we always have the option to use table A2, which we've been practicing with since chapter 6. If you do want to use your TI-83 or 84 calculators, the command is stat tests and then the one proportion z test. Unfortunately, the TI-36X Pro calculators do not have this option. So if you have a TI-36X Pro, the preferred method is to use table A2. For critical values, the best way to find the critical values is to use table A2. Although calculators do have the inverse norm command, I find it quite tedious to use, and I do prefer using the tables. It's a little bit more straightforward. Let's walk through an example. The PowerPoint slides were created by the textbook authors, so they're structured in a way that differs from what I prefer. So I am going to write up this example with my own handwriting and post it to Canvas so that you could see what we walk through in the PowerPoint slides, how that translates into what I would expect of you in a write-up. But let's go through the more thorough PowerPoint slides for understanding, and then I'll show you how to present it in a more concise way later on. In this example, we have a study of sleepwalking or nocturnal wandering described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. So this is data coming from a sample. The sample has 19,136 individuals. That will be our sample size. And in that sample, 29.2% reported sleepwalking. That is going to be our p-hat, which we'll write in decimal form. Would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Well, this is a claim about the population proportion P. This claim is that fewer than 30% of all adults have sleepwalked. So we're making a claim about a population parameter, namely P. Let's use a 5% significance level to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.30. The original claim is expressed in symbolic form as the population proportion P is less than 0.30. This is a clear indication that we have a direction, namely this is going to be a left-tailed test. Because the claim is in the form of an inequality, that is going to become the alternative hypothesis. Remember, the alternative hypothesis is always a statement of inequality. The counterclaim, the null hypothesis in this case, is a statement of equality, that P is equal to 0.30. Recall that the two statements don't have to cover all possibilities. For example, if P were greater than 0.30, that wouldn't be covered by either one of these statements, and that's okay. As long as we have an inequality statement in the alternative and an equality statement in the null, we have the ground covered. So again, because of the direction of the alternative, this is going to be a one-tailed test, and it will be specifically a left-tailed test. We are told to use a significance level of 0.05, so alpha will be equal to 0.05. Because the claim involves the proportion P, the statistic relevant to this test is the sample proportion p-hat, and the sampling distribution will be our standard normal distribution, which is the distribution of z-scores. As I stated earlier, this will always be the case when we're working with proportions or percentages. First, let's calculate our test statistic z. Using the formula described earlier, z is equal to the population proportion p-hat minus the claimed value of P that appears in the hypotheses divided by the standard error. So we were told that 29.2% of the sample reported sleepwalking. That's going to be our p-hat in decimal form. We have a mistake here actually. This should say 0.3. I'm not sure why it says 0.5. The hypothesized value of P is 0.3. So please make sure that you correct that in your notes. They do have it correct here in the denominator. This is P, this is Q, which is 1 minus P, and here is our sample size. I do believe this calculation is correct. The typo is simply right here in where 0.5 should be 0.3. So we get a negative test statistic Z, negative 2.41. Because this is a left-tailed test, the p-value is going to be the area to the left of that test statistic in that left-hand tail. Using table A2, we simply have to look up this z-score and find that the area to its left is equal to 0.008. So that then becomes our p-value, 0.008. Because the p-value is less than our significance level of 0.05, this says to us that we have sufficient evidence to reject the null hypothesis. In rejecting the null hypothesis, we are finding evidence against the claim that the percentage of sleepwalkers is 30%, and in doing so, we are finding support for the alternative hypothesis that fewer than 30% of all adults have reported sleepwalking. So here's the interpretation. Because we reject the null hypothesis, we have sufficient evidence against the claim that 30% of adults have sleepwalked. Equivalently, we have sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked.